Part 2 of representing molecules is the drawing of Lewis structures and using formal charge to determine the best Lewis structure. And then finally we will look at a few of the so-called exceptions to the octet rule, which in general I don't see them as exceptions of the rule, but as applications of the rule that I showed you in part 1, where first period elements can only form one bond, second period elements can form up to 4 bonds, third period elements up to 9 bonds, etc. Step 1 in drawing Lewis structures. The first thing to do is to draw the skeletal structure of the compound, showing what atoms are bonded to each other, and then to set up an electron accounting table like the one shown below. Note that when you are setting up your skeletal structure, hydrogen and fluorine will always be on the outside. They are terminal atoms. We will generally put the least electronegative element in the center unless otherwise designated. The generic table that you see below has the central atom as being the first atom, and following that are the peripheral atoms. There is an overall charge column that is useful for ions and polyatomic ions, and then finally there's a total charge, a total electron column where we account for all the electrons, ensuring that we're not losing any. Row 1 is for the valence electrons. This way we know exactly how many electrons are in the structure. Row 2 accounts for any bonds. Row 3 accounts for lone electrons. And then finally there is a formal charge row wherein we will look at the formal charges on all the atoms, try to get them to be as small as possible given the constraints of the various rules for each element in each period of the periodic table. Here's step 1 for carbon dioxide. Carbon is the less electronegative of the two, so it goes in the middle. Each oxygen is attached to the outside. Then we set up the accounting table with carbon in column 1 and each of the oxygens in a following column. Since this is not a polyatomic ion, we really do not need the overall charge column, and you could get rid of that for this structure. And then finally there's the total column, where we will make sure our counting of electrons is done properly. Step 2 in drawing Lewis structures is to count the total number of electrons for the structure by summing the valence electrons for each atom and then adding 1 electron for each negative charge and subtracting 1 electron for each positive charge. For carbon dioxide, you can see that the valence electrons are listed here. We can actually count the number of valence electrons by looking at the group on the periodic table. Carbon is in group 14. 14 has 4 valence electrons. Oxygen is in group 16. They have 6 valence electrons each. Since this is a neutral molecule, there's no overall charge. Totaling those up, we have 16 electrons that we have to account for on the structure. Step 3. Basically, we're going to start with the accounting of the electrons. We're going to subtract the bonded electrons, because there are 2 electrons in each bond, from the total count in step 2. And then we're going to distribute the remaining electrons as lone electrons by first completing octets on terminal atoms, except hydrogen, because it's in period 1 and only gets a duet. And then we will place any remaining electrons on the central atom. Note that each peripheral atom, because it already has one bond, will get 3 sets of lone pairs for a total of 6 electrons each, making sure that your accounting is well taken care of. When we do this, what we will do is we will start with the peripheral atoms, and then we'll go to the central atom if necessary. So looking at carbon dioxide, we start out with 16 total valence electrons. There are 2 bonds. 2 bonds is a total of 4 electrons, but here's how we account for them on the table. Carbon has 2 bonds because it's sharing 1 electron to each of the 2 bonds. Each oxygen shares an electron to the bond, so the 2 plus 1 plus 1 should equal 4, and we are accounted for on the bonds total. That leaves 12 valence electrons that have to be distributed around the structure. First by putting 6 on each of the peripheral atoms, and then if there are any left over, putting the rest on the central carbon. So seeing there are 12, I'm just going to write in here a 6 under each oxygen, going from right to left. Notice that that takes up all 12 of the electrons, leaving no electrons to go onto the carbon. And here's what our structure looks like. Here are the lone electrons on each oxygen. The 6s with no lone electrons on the carbon. Making sure it's right. 0 plus 6 plus 6 equals 12. 2 plus 1 plus 1 equals 4. And note here, 16 minus 4 minus 12 ends up being 0. We've accounted for all the electrons on the table. Step 4 in drawing a Lewis structure is to calculate the formal charge on each bond. We do this so that we can then determine whether or not double bonds or triple bonds are necessary for our structure. The formal charge is calculated by taking row 1, the valence electrons, and subtracting row 2, the number of bonds, and subtracting row 3, the number of lone electrons, to give us the formal charge in row 4. Note a couple of other special things. That is the overall charge has to be the sum of all the formal charges. In addition, we still have to make sure that our total comes up correct. So here's step 4 for carbon dioxide. We have on the carbon 4 valence electrons. 2 are in bonds. It has no lone electrons. So 4 minus 2 minus 0 is plus 2. So the carbon has a plus 2 formal charge on it. For each oxygen, they have 6 valence electrons, minus 1 for the bonds, minus 6 for their lone pairs, giving each a formal charge of -1. Summing up the bottom row, 2 minus 1 equals 0. 16 minus 4 minus 12 over here on the right-hand column equals 0. Our accounting chart shows that we've accounted for all the electrons and the charge, and we have a good start on our structure. However, this structure has a lot of formal charge. We do not like formal charges on our structure. If we can get rid of them, we will. With polyatomic ions, we generally cannot get rid of a formal charge. It inherently has some. So they have to be somewhere. Typically we want them on the most electronegative atoms. So if we have to have a formal charge, let's say on carbon dioxide, we would put it on the oxygen. In step 5, we will reduce our formal charges, especially on the central atom, by creating doubles and triple bonds. Usually the central atom has a positive formal charge because it is the least electronegative, and negative formal charges tend to be on the outside, though this is not always the case. To reduce the positive formal charge, we look at an atom sitting next to the central atom and move a lone pair from one that has a negative formal charge and create a double or triple bond between the two atoms. What this does is it moves an electron into a shared position so that the formal charge on the positively charged side goes down and the negatively charged side goes up, effectively reducing the formal charges. You must remember a couple of things. In our effort to reduce all formal charges to 0, we cannot break the octet rule for second period elements because they have only s and p orbitals and cannot hold more than 8 electrons. In elements in the third and fourth periods and beyond, they can hold higher numbers of electrons, so it is possible to move electrons to form 10, 12, 14 electrons around central atoms in third, fourth, and fifth period elements. Note a couple of special cases regarding second period elements. Beryllium typically only forms 2 bonds. When looking at beryllium compounds, we'll find that once they are built, the formal charge on the beryllium is 0, and there really is no need to reduce the formal charge. Just leave it as it is. For boron, it usually only forms 3 bonds. Again, here we see that with boron, it's going to have a 0 formal charge with 3 bonds, but occasionally it will form a 4th bond, especially in compounds where it has what is called a coordinate covalent bond, where electrons are supplied to make a 4th bond, and it's not really sharing electrons, it's borrowing electrons, and the boron oftentimes achieves a negative formal charge as a result of this type of bonding. So looking at our Lewis structure for carbon dioxide, we see this +2 formal charge in the middle and a negative formal charge on the left-hand oxygen. We can move one lone pair in to create a double bond between the carbon and the oxygen on the left. And we can also, because there is a 2+ charge, reduce this negative charge by moving a lone pair of electrons to create another double bond in the middle, resulting in a structure that looks like what we would think carbon dioxide would look like, with carbon having 2 double bonds, 1 to each oxygen. Let's note that on the central carbon, it had a +2. It gives us kind of an indication that 2 additional bonds need to be formed. To confirm that, we would look at the 2 oxygens to see that there are 2 negative charges to work with. Thus we can see 2 more bonds can be formed. Now let's review our valence electron accounting table for our new carbon dioxide structure. The valence electrons that each of the atoms brings to the structure does not change. Carbon's still 4, each oxygen is still 6. There's still no overall charge for a total of 8 electrons. Carbon now has 4 bonds, 2 on the left and 2 on the right. Each oxygen has 2 bonds. Added up together, we get 8 electrons that have been used in bonds. For lone electrons, the carbon has 0. The oxygens on the right and left each have 4, for a total of 8 electrons. And 16 minus 8 minus 8 is 0. All of our electrons have been accounted for. For formal charges, for carbon, 4 minus 0 is 0. Oxygen, 6 minus 2 and minus 4, those are 0. They're all zeros, they add up to 0, and the counting on the formal charges is complete. In some cases, more than one structure can be drawn, especially in cases where double bonds can be formed in different locations on a molecule. We can then draw what are called resonance structures. Molecules with no formal charges at the end of drawing do not need to go beyond step 5 to find possible resonance structures. This is the case with carbon dioxide. However, we could have drawn the carbon dioxide molecule a little differently, one where we reduce the 2+ formal charge on the carbon by moving 2 lone pairs from either the oxygen on the left or the oxygen on the right, creating these 2 new structures where there is a triple bond and a formal positive charge on one oxygen and a formal negative charge on the other in both cases. These aren't the best structures, but they're possibilities that could occur, and we would call those resonance structures. If resonance structures do come about, we want to choose the one with the fewest number of formal charges. We want negative formal charges to be on the more electronegative atom, and we want positive formal charges to be on the less electronegative atoms. For carbon dioxide, this top structure is the best structure because it has no formal charges. The second structure has 2 formal charges, and the third structure has 2 formal charges. They are really not good structures for us to use. In addition, there's this formal charge of a positive on oxygens, and oxygens generally do not like to have positive formal charges, though it will happen on occasion. Next, we will draw the Lewis structure of the carbonate ion so that we have a polyatomic anion for us to work with. In step 1, we're going to draw the structure. We're going to put the carbon in the middle because it is the least electronegative. Put the 3 oxygens on the outside. And we are also going to be dealing with an overall charge because carbonate has a -2 formal charge. Next, we are going to put in the valence electrons and the overall charge. 4 for the carbons, 6 for each of the oxygens. The overall charge is -2. So when we're counting for valence electrons, we actually have to add 2 electrons for the formal charge for a total of 24 electrons. Then we're going to count the bonds. Carbon has 3 bonds. Each oxygen has 1. The total number of electrons in bonds is 6. This leaves 18 electrons to distribute as lone electrons in sets of 6 around the structure until we run out, and if we have any left over, we put them on the carbon. However, there are 3 oxygens. each getting 6 lone electrons, to take all 18, leaving none for the carbon. Now looking at the formal charges, for the carbon, it's 4 minus 3 gives us a plus 1. For each oxygen, it's 6 minus 1 minus 6. Each one of those is negative 1. As we can see, we've drawn those on the structures. And then if we add up the formal charges along the bottom row, 1 minus 1 minus 1 minus 1 is minus 2, which is what we would expect for the overall charge. And just to check, 24 minus 6 minus 18 is 0. We've accounted for all of the electrons in the structure. Next, we need to reduce the formal charges, and what I've done is I've moved the lone pair of electrons from the oxygen on the left and placed it to make a double bond with the carbon. And what this has done for the formal charges is the following. Carbon now has 4 bonds, no lone pairs, formal charge is 0. This oxygen here has 2 bonds, 4 lone electrons, for a formal charge of 0. And then there are these 2 other oxygens left over that have formal charges of -1 each, for a total of -2. And we would expect that there would be formal charges somewhere on this structure, given the fact it is a polyatomic anion. Since there were 3 oxygens, each having a negative charge, next to the carbon that had a single positive charge, we could have formed that double bond in any one of the 3 positions. Here to the left, here to the upper right, or here to the lower right, creating 3 resonance structures for the carbonate anion. In resonance structures, basically we have 2 or more Lewis structures for a single molecule that cannot be represented accurately by one Lewis structure. This top example is ozone. We cannot get 2 double bonds on that central oxygen to reduce these formal charges here, because the oxygen already has an octet. 6 from the bonded atoms and 2 from the lone pair. Because it's a second period element, we can't reduce that formal charge any further. As a result, we can put the double bond on the left or over here on the right, resulting in 2 Lewis structures. That, however, is not really what we see in nature. And again, showing the carbonate ion, the 3 different positions below on the carbonate ion. But again, this is not how nature views the molecule as 3 separate entities. In the carbonate bonding, we can kind of merge the 3 structures together into this thing called a resonance hybrid. It's a Lewis-like structure that distributes the negative charge over every place there was a formal negative charge by its average. And on average, this one at the top has no formal charge and then has a -1 formal charge 2 of the 3 times. Same for the one on the lower left and the lower right. They have a negative charge 2 out of 3 times for a -2/3 charge. This single solid line in the Lewis-like structure, or the resonance structure, represents 2 electrons, and the dashed line represents any number less than 2 electrons. It could be 1 electron shared between 2 oxygens. It could be 1/3 of an electron. It could be 2/3 of an electron. In our case, there are 3 bonds, and there's one electron shared amongst 3 bonds. So basically it's like 1/3 bond between the two atoms. Here's a space-filling model of the carbonate ion, and as you can see, you cannot tell one oxygen from another. There aren't any size differences, any bond length differences, any charge differences amongst the 3. And now for the so-called exceptions to the octet rule. And as I stated before, I really don't view these as exceptions to the octet rule. I really view them as part of the rules of forming Lewis structures and realizing that if you reduce formal charges and get the best structure, you're going to stop when formal charges are 0. Again, for beryllium hydride, BeH2, the beryllium contributes 2 valence electrons. Each hydrogen contributes 1 for a total of 4 valence electrons. It makes 2 bonds. It's called an incomplete octet, but to me it's the way it should be. Boron trifluoride that we see down here. Boron is 3 electrons. The 3 fluorines is 21 electrons for a total of 24. You have 6 in the bonds, and then you have 18 more lone electrons on the fluorines. That accounts for all of them. When you calculate the formal charges, they're all 0. There's no need to do anything more with this structure. Odd electron molecules, again, it comes down to the formal charges. If you get down to formal charge of 0 and you have one electron that's not paired up with another, that's perfectly fine. Typically these will occur with elements that are in odd numbered groups, like group 15 where nitrogen is. Since it brings 5 electrons, an odd number, and if there's only one of them and it's not and it doesn't have an additional electron from another nitrogen, which is an odd electron, or doesn't have a formal charge, or isn't a polyatomic anion or such, then it's going to end up with an odd electron. Well, where do you put odd electrons? You put them on the atom that tends to be from the odd numbered groups. For sulfur hexafluoride, we've seen this before, where the central sulfur has 12 carbons surrounding it. However, that's expected to happen with a 3rd period element. Just to remind you that a 3rd period element has an s orbital, 2 electrons, p orbital, 6 electrons, d orbital, 10 more electrons. It can have a total of 18 electrons around it, so going up to 12 is easy for it to do. And it does this by incorporating d orbitals into its bonding pattern, which we will see in the next chapter.